Let's talk about this idea of resistivity. And resistivity is just going to be it's a characteristic of any material, and it's the same for the material. The resistivity is the same for the material all the way through. Okay, so we're looking at resistivity, and it's the way that it'll go again, it'll provide resistance on the current as it's passing through. The resistance, the total resistance, is a combination of the resistivity of the material, the length of material that the current is passing through, and then the overall, it's the cross-sectional area, so that the current's passing through. And so those three things together provide the overall resistance. And so we can say that resistance, the equation we'll be operating with, is that resistance is equal to rho times L over A. And so when we're setting this up, you have your resistance. It's still measured in ohms. And so if we want our resistance, it's this combination of these things. And so the resistivity is this. And so I'll just draw an arrow there since I wrote it too high. Resistivity is rho. It's sort of that kind of smooth curly P. It's the Greek letter rho. Length of the material. And then this is the cross-sectional area of that. It's usually going to be a wire. So cross-sectional area. And so this is looking at the idea that even though frequently most of the time, we're going to calculate a circuit and not pay attention to the resistance of the wires. Usually the wires will have a low enough resistance that you can do everything else you need to within the circuit without paying, relatively, they're not going to add enough within the resistance of the overall circuit to make a difference. However, they still do. There is some resistance that's there by the wires, and the longer the wires are, the more resistance that you're going to have. This is why they make wires of really specific material, because you want to have a material that has a really low resistivity that allows the current to go through without messing with it too much. And depending on which metal you use will depend on what kind of outcome you'll get with that.
What video do I have to watch?
The other thing that you have is that you get to pick. The other thing that you have with this area is the way that the current travels is dependent on that area. Think about water traveling through a pipe. If you have a really, really, really tight pipe, it's going to restrict the amount of water that you can get through. If you have a really wide pipe, that water can flow really easily. And the same thing happens in the way of resistance and the way that the cross-sectional area of that wire works. If you have a teeny, teeny, tiny, tight wire, that area is really small. And with that area being really small, you can't get as much current through there. However, if you have a really wide wire, again, you have to kind of look at the idea of what's actually beneficial to what you're building, and then what is happening within the resistance of the wire itself. But if you find that balance and you have a larger area, it will allow for a lower resistance here. And so because there's more space for that current to flow. So that relationship is what we're looking at in this situation here. When we set this up, we have our wire here. And you have your length is just whatever the length of that wire is. Has to be measured in meters. Yeah. We'll keep everything in meters. Sometimes your resistivity, they'll talk about dealing with centimeters. And I said, you could keep them, but if you keep them both in centimeters, that can work as well, because those if you kept all of it in centimeters, you can do it because they'll cancel out, but we'll talk about that in a little bit. You have your radius on that cross-sectional area. And remember that A is equal to pi r squared. And so depending on what information you're given, you'll either be given the area as is, or you'll be given the radius and then need to calculate the area. And so you're looking at that cross section. If you cut it off, it's like if you cut off you cut down a tree, that kind of that area of the stump there, that's what we're kind of talking about here. And then you have resistivity, which is that tendency to resist the current. And so a higher resistivity means it's resisting the current more. So when we talk about resistivity is measured in ohms times meters. It's not ohms per meter. It's ohms times meters. And so this is there's a couple of things that go along with this when it comes to the way that we talk about it. It's easily confused in a couple of different ways. First of all, the verbiage of resistance and resistivity. It's really easy to confuse those two or to accidentally say or write the wrong one. Resistivity, a lot of times when we're measuring something, it's something per something, and this goes against that. We've got ohms times meters, and I'll show you where that comes from in just a minute. And so when it comes to the way that you'll write up your lab, one of the things you'll need to be thoughtful of is using the right verbiage and the right units in what you're doing. And that's part of why we practice with this one. With resistivity, let's rearrange this equation to solve for resistivity.
What happened?
And if we do that, and I'll slide this up in just a moment, we have rho is equal to R times A over L. And so we have that rearrangement here. And we know that our resistance is equal to ohms. Area is measured in meters squared, and length is measured in meters. And so when we take the units that make up the resistivity, so it's a combination of the overall resistance that you have and the area, the cross-sectional area of that wire. It's a combination of those two and then divided by that length. And because of that, because this is how it's structured, the squared cancels out there, the meters cancel out there, and you're left as a unit for rho of ohms times meters. And so again, it's one of those detail pieces that helps you communicate correctly in what you're doing. Can you go plug that? So keep that in mind.
What?
And can you go plug that in, please? My computer's not plugged in. So keep that in mind kind of as you're looking through things. In general, the way that these problems go, it's a pretty straightforward equation. You're able to say, oh yeah, okay, well I know the resistivity and the length and the area, or I know the resistivity, the length, and the radius, so I can get the area and get what I need. So in the way of calculation, it generally goes pretty well. I'll leave this here for a minute. If you want to screenshot that, and then I'll slide it up to get the bottom part if you want to screenshot that. My dog's talking quite a bit this morning. She's got things to say. There we go. So I'll take this part off. And I want to talk about this equation in the way of graphs. And so we know we have R equals rho L over A. And in the lab that you're going to do, you'll actually choose which one of these you want to work with this week. And then kind of graph from there. They're both pretty straightforward in how you can do your data in the graph. But if you're measuring resistance and you pick, let's say we look at length for your independent variable, then when you graph, if you have your length here and your resistance here, you should have a linear slope. And from that linear slope, it should be equal to rho over the area when you graph that. Same thing if you have, if you make your independent variable as rho, if you change the resistivity on there. This is where working with a simulation can work well. If we say rho L over A, and we put rho on the bottom here, then our slope here would be L over A. And so depending on what you have and depending on how it is set up, depending on what your variables are, you can draw value from that slope. The other way that this might set up is if you're making area your independent variable and measuring resistivity. And then you would have, let's do this, rho L over A. You could do that as rho times L times 1 over A. And so you would say your resistance, oh yeah, I want that there, resistance. And if you had area, um, it would look something like this. And then if you said resistance over 1 over A, you would get your linear slope, and that slope would be rho times L. And so this equation works really nicely when we're dealing with it graphically, because we can tie back what we know and be able to figure out something here. And so I want to talk a little bit about the lab and